Hi everyone. In this talk, I'm going to introduce our recent work in using statistical model checking to verify the safety of learning-enabled cyber-physical systems. So cyber-physical systems are usually composed of a physical plant controlled by a cyber controller through actuators and sensors. They have wide applications in medical devices, autonomous cars, bipedal robot, and drones. These systems are usually dependent on learning-enabled components such as neural networks in order to process high-dimensional sensing data or to deal with complex dynamics or to make smart control decisions. The safety of these learning-enabled controller is a big issue because cyber-physical systems are usually working in safety-critical environments. In addition, these learning components are usually learned from samples, and there's usually little guarantees on their behavior out of the training set. In addition, these components may have been learned for some surrogate reward that does not directly align with the safety specifications. Finally, the complexity of these learning components like neural nets can pose a challenge in analyzing their safety. So in this work, we develop a new statistical model checking algorithm to check the safety of learning-enabled cyber-physical systems. We apply these new SMC algorithms to verify the safety of three case studies: the mountain car, bipedal robot, and magnetic levitation. In this work, we consider a probabilistic plant. The probability in the plant may come from system noise, uncertain parameters or initial conditions, or the random faults in the wireless communications. We want to check whether a learning-based controller can guarantee the safety of the whole system with high probability. That is to say that we want to check for a random path of the cyber-physical system if this path is safe with probability greater than some threshold p. To formally capture the safety of a random path of the cyber-physical system, we introduce the signal temporal logic. A signal temporal logic specification is constructed inductively using the following four rules, where the first rule is called the atomic proposition. It is the basic building block of signal temporal logic. It states that a function value of the system path is greater than 0. And then these building blocks can be concatenated using negation, disjunction, or the until operator. The meaning of this until operator, phi until psi, meaning that phi should holds true until psi becomes true, and this change should happen between the time interval t1 and t2. Using these basic operators, we can express more meanings like finally and always. The advantage of using temporal logic is first, the syntax of the signal temporal logic is very simple. It's composed of only 4 inductive rules. In addition, the semantics of STL is rigorous, meaning that for any STL specification, there is only a unique way to interpret its meaning. In addition, it is very expressive in expressing temporal behaviors. So, we have shown that it can express until, finally, and always. This is generally more expressive than, for example, safety region, barrier function, etc. So having expressed the safety of a path by signal temporal logic, our problem basically becomes whether for a random path from a cyber-physical system, the satisfaction probability of sigma to phi is greater than the probability threshold p. To check whether a random path from the CPS satisfies the STL specification with probability greater than p, we use statistical model checking. The general idea is to draw samples from the system and estimate this satisfaction probability from samples. Specifically, let sigma I be a bunch of samples, IID samples from the CPS. On each sigma I, we can verify whether the STL specification holds or not. This is based on the assumption that phi can be checked on sigma I for a bounded time horizon. Then we can construct an empirical estimation on the satisfaction probability. From basic statistics, we know that this PM bar is an unbiased estimator of the true satisfaction probability. Therefore, our statistical assertion should be if PM bar is greater than P, then we should say the satisfaction probability should be greater than P. and similar for the other case. The advantage of statistical model checking is that it is model-free. Therefore, it can handle black box systems with unknown dynamics. In addition, it is scalable to high-dimensional systems and can avoid the curse of dimensionality. But there is still one remaining question. If we would want our statistical assertion to be correct with high probability, namely greater than 1 minus alpha d, what should we do? So here we call alpha d the significance level. It is the maximum probability that the SMC algorithm returns a wrong assertion. To answer this question, we first consider the significance level of this statistical assertion for n given samples. This is done by using the Cloper-Pearson method as follows, and this is the main novelty of our SMC technique. Based on this, we can construct a sequential SMC algorithm that can achieve any desired significance level alpha d. This is done by drawing more samples at each iteration and compute the Cloper-Pearson confidence interval alpha CP. And the algorithm only terminates when alpha CP is less than alpha d. Under the assumption that the actual satisfaction probability is not equal to the probability threshold p, then we can show that the algorithm terminates with probability 1 because the Cloper-Pearson confidence interval alpha CP always converges to 0 as the number of samples increases. In addition, whenever the algorithm terminates, the return answer has significance level less than alpha d. Therefore, the overall significance level of the sequential SMC algorithm should be less than alpha d. Now we apply our SMC algorithms to verify the safety of several benchmarks. The first benchmark is the mountain car. The car starts from the bottom of a valley and tries to reach the top on the right. The challenge is that the car's engine is not strong enough. Therefore, it needs to move back and forth to build up momentum. The dynamics of this car is given by this first-order differential equation with the value of the parameters given as follows. The neural net-based controller of this car is learned through this actor-critic architecture using the surrogate loss RT given below. So having derived the neural controller, we would like to verify its safety. The safety specification is given by whether the car reaches the top within time delta with probability at least 1 minus epsilon, where epsilon and delta are given below. The initial position of the car are drawn from these Gaussian distributions, and we run our SMC to check the correctness of these safety specifications with significance level 1% or 5%. Here is a figure showing the dependence of whether the car reaches the top with its initial position. And here are two concrete executions on the satisfaction and failure of reaching the top. To verify the safety of the mountain car, we draw samples from its Simulink model. The safety property is verified for different setups of the parameters. We know that an SMC algorithm may return a wrong answer with probability at most alpha, the significance level. To validate this, we repeat each SMC task 100 times and estimate error probability. We can see that the actual error probability is less than alpha in most cases except for one situation. We believe this is because of the statistical error from the estimation for 100 repetitions. And from the SMC result, we believe that we know that the mountain car reaches the top with probability 0.9 for a time horizon between 7 and 10. Our second case study is this bipedal robot. It is a more complicated dynamical system than a mountain car with 5 links and 25 joint variables. The dynamics of this bipedal robot is given as follows. Again, we learn a neural net-based controller of this bipedal robot using the actor-critic architecture using a surrogate reward function like this. The actor neural net has 4 layers and the critic neural net has 6 layers. And now we verify the safety of this learned neural net controller for the bipedal robot. The safety specification is given by this long STL specification. Here, eta1 means that the bipedal robot moves out of track. The second, eta2 means the robot fallen. And the third one means that the orientation of the robot is very bad. Again, the initial position of this bipedal robot is drawn from these Gaussian distributions. We verify this safety specification by drawing samples from the Simulink model of the bipedal robot, and we verify this safety specification for different setups of the parameters. From the result, we learned that this bipedal robot, the learned controller, will fail with probability 88% during a time horizon between 2.4 and 3.0. Our third case study is the magnetic levitation system. Basically, it manipulates the motion of an object through magnetic field using the following feedback control diagram. The goal is to stabilize the motion of this object to some desired position, and the deviation from the desired position is captured by the integral absolute arrow IAE. The motion of this object under the magnetic field is given by the second-order nonlinear equation, and the neural net controller has 7 hidden layers and 5 nodes per each layer. Again, we verify the safety of this magnetic levitation system by drawing samples from its MATLAB Simulink model, and here is a sample path for IAE over time. The safety specification of this magnetic levitation system is captured by the following formula. We want the IAE to be less than delta for a time horizon from 0 to 5 with probability at least 1 minus epsilon. We have verified this safety property for different values of delta, epsilon, and alpha. And for each verification task, we estimate the error probability of the SMC algorithm. We've seen that in most cases, the estimated accuracy of the SMC algorithm is consistent with the significance level except for one case, which again we believe is due to the statistical error of estimating from 100 repetitions. So from the verification result, we know that the IAE will be less than some value between 1 to 1.1 with probability 50%. Now I would like to conclude this talk. Our first contribution is to propose a new statistical technique for verify the safety of learning-enabled cyber-physical systems. These safety properties are expressed by signal-temporal logic. In addition, we have shown that our statistical model checking algorithm can be used to verify the safety of real-world cyber-physical systems, such as the mountain car, bipedal robot, and the magnetic levitation systems. In all these case studies, the safety property can be verified with high statistical accuracy in a relatively short amount of time. Finally, I would like to mention that our SMC method for STL specification is very general. In addition to neural network controlled cyber-physical systems, the SMC method can also be used to verify the safety of black box or complex cyber-physical systems. In addition, beyond safety specifications, other STL specifications can also be verified using our SMC algorithm. This is the end of this talk. Thank you for your attention. If you have any question, please feel free to contact us by email.